Hello, my name is Frank Revisa, and today I'll be giving you a brief introduction to the double Gauss lens. The double Gauss lens is a very important photographic objective because it is so extensively studied. There is over 100 years of design history on the double Gauss. There is new designs in the pipeline today, and I couldn't find a record of how many have been produced, but if you consider smartphones likely have a lens design that's based in the double Gauss, I would guess it's in the millions. And here's a cross section on the right side here of some of the double Gauss lens designs over the past 30 years. Some of them down to f numbers below 1 in the Noctilux f.95. The reason why the double Gauss is so important is it's able to control all fourth order wave aberrations, and it is limited only by higher order aberrations. Performance is generally excellent, assuming it's been optimized correctly. Extremely wide apertures are possible, as in the Leica is an example of that today. That's a modern, super fast double Gauss lens. It is flexible, which means it's often a good starting point for for a lens design. The double Gauss gets its name from the mathematician Carl Friedrich Gauss, and it's really only loosely based on Gauss's solution to the doublet, which Gauss took the Fraunhofer doublet, which is considered the best solution for a doublet, and added turned the second element into a strong meniscus, and the purpose of this was to correct spherochromatism. However, in the process, he added zonal spherical aberration, coma, and astigmatism. Gauss envisioned this objective to be used as an astronomical objective, and Alvin Clark attempted to do this, but failed. However, Alvin Clark in 1888 arranged two Gauss lenses symmetrically about the stop. And the advantage of doing this, the significance of doing this, is it naturally corrects odd order aberrations, coma, astigmatism, and distortion. Clark's patent in 1888 is the first record of a double Gauss. However, its performance was degraded by field curvature. 10 years later, Paul Rudolph thickened the inner meniscus lenses and added buried surfaces to correct for color. The thick meniscus corrects field curvature, and due to these contributions, Rudolph is generally recognized as the inventor of the double Gauss. Later, as higher index materials became available and lens design techniques improved, Taylor and Hobson designed an f2 photographic objective 1920. And this was the first commercially successful double Gauss lens. The purpose of the asymmetry was to balance the higher order aberrations. Some recommended reading on the double Gauss if you're interested in learning more about this, and this is where most of my source material comes from, are these three papers here. An important contributor to the double Gauss is Walter Mandler, and two of those papers are from Mandler. And he was a prolific physicist and engineer. He was German-born, but moved to Canada, to the Leeds Camera, Canada. And from 1965 to 1985, he was the head of optical and mechanical engineering at Leeds. He contributed to over 400 lenses, and those were used in photography, of course, and also for military customers. He designed 50 Leica camera lenses. Some of them are still manufactured today. And his main contributions were in pioneering computer optimization techniques. He was very much at the cutting edge during his day in computer design. And here's an example of one of his lenses. This is the Noctilux. So this is the earlier version of the Noctilux that was designed in 1969. It was designed without computer optimization, which I think is impressive. And the Series 2 lens, which is essentially the same lens design that you're seeing here, is available for sale right now for $7,700 on eBay if anybody's interested. And the double Gauss procedure that Walter Mandler published as his PhD thesis in 1979 describes a triplet model for the double Gauss, and this is a convenient way to conceptualize the double Gauss. I couldn't figure out which person in this photograph is Walter Mandler. I would guess he's the person in the middle there. So here's what the triplet model looks like. So you can think of it as a cooked triplet. However, the center negative element is split into two negative meniscus lenses. And I'm also showing a buried surface in here. And the purpose of that buried surface is to correct color. And you do this by having two cemented elements that have equal index of refraction but different dispersion characteristics. And that dispersion characteristic allows you to correct chromatic aberrations. The relative powers of the three lenses are equal to 1 in this model. And the system is symmetrical about the stop. It's important that you set the Abbe numbers of this is more of a rule of thumb, but I've verified that it's a good rule of thumb through my work in optimization of the double Gauss. You need to have the Abbe numbers of the buried surface have a ratio of around 2/3. So based on this triplet model that Gauss has provided, or Mandler has provided us, I've come up with a optical design procedure for the double Gauss lens, starting from scratch from a paraxial layout, if you would like to take it to that level. However, I've modified Mandler's publication, Mandler's procedure to take advantage of modern optical design software, such as Zmax. So it's pretty simple. You start with a paraxial layout. You could probably omit that step. And then you select 3 glasses, and I'll go into what glass materials you should select. And then you convert the paraxial lenses to thick lenses, and then you can split the central negative element into 2 menisci. And then you convert the menisci into doublets. And the next step is to begin some optimization across the field. And this is done through just a rough solution of a symmetrical system. And then when you get to step 7, you can break symmetry and begin to optimize further using 14 variables. And finally, in step 8, you can do some fine tuning to achieve higher performance, such as splitting the meniscus, the first meniscus, vignetting the pupil. You could add elements and aspheric surfaces if you want to increase the aperture, or you could substitute glasses. And then finally, step 9, which I won't talk about at all, you would need a tolerance, design the optomechanics, manufacture. That's probably the most time-consuming step, but we're mainly interested in the optical design in this presentation. So as an example, we'll design a 50mm lens, and I've based the requirements around the Canon 50mm f1.8. This is a relatively inexpensive plastic housing lens. It costs $100. I own one myself and have used it to make some nice photographs. Here's a listing of the requirements. It's based on a 35mm film plane, and today would be a 35mm format CCD. And then from that follows the field of view and thickness specifications, focal distance, etc. And also Canon publishes some MTF data on their website. And then this table up here essentially takes the MTF curves versus field here and lays them out. So those will be our target MTF values. So step 1, and you can skip this step, but if you're interested in learning the double Gauss, it's nice to see how this lens lays out in terms of a triplet model. So here's a spreadsheet I wrote that gives you the solution for the focal lengths given a effective focal length for your double Gauss lens and a desired back focal length. And from the triplet, from the paraxial triplet layout, you can turn that into a thick triplet. Here's a table of radii and spacings, lens thicknesses for the thick triplet model. So the next step is to select your glasses, and you need 3 different glasses. Generally, the higher the index, the better. However, the Abbe number of of glass C must be 2/3 of the Abbe number of B. And for this example, I've selected some very high index glasses just for fun to achieve as high a performance as possible. So here are those glasses, index up to 1.9, which is very high. And the ratio of B and C here is 1.47. So we're very near that ratio of 2/3. And some glass refinements for later, once you have a decent solution. If you're interested in improving performance incrementally by tweaking the glasses, you can substitute a lower index glass in the first element if you want a lower cost. That generally produces less degradation to performance than lowering the index in the final element. It's best to maintain the buried buried surface, meaning don't have an index variation across the cemented surface. However, if you do break the cemented surface on the first meniscus, you can have a slight index variation, and that can lead to an improvement in coma performance. And you can also vary the index of refraction across the lens to improve the Pestfall correction, and some lenses take advantage of that. And that's an alternative method to changing spacing. So in terms of glass selection, it's best to use the Abbe diagram. I'm generally a graphical person, so if you could kind of lay out which glasses you want. So you can see B and C, they have equal index here, and they have a 2/3 ratio to their Abbe number. And then I've selected a very high index glass here for glass A. The next step is, of course, turn that triplet into a monochromatic thick triplet using glass C. And this solution was also obtained in Excel, but you could use lens design software. So here's the analytical solution to the radii of curvature. And step 3, you need to split the central negative element into 2 menisci. And a rule of thumb, a guideline that I've found that seems to work, help the optimization software later on, is to use a shape factor of approximately 2. And that equates to a ratio of 3 between radius 3 and 4. And there are some constraints you need to add to your lens software to keep it behaved, and here's a listing of those. You need to use lens, of course, radius pickups and thickness pickups to maintain symmetry, and take advantage of your software's ignore this surface feature, or its equivalent. It's called ignore this surface in Zmax. So you can set radii curvature of individual elements. And don't worry too much about spacing yet, other than the back focal length and the effective focal length. So now we need to substitute our glasses, and here's our table of glasses here. And this is where they go. Remember, we have symmetry, so each the radii of curvature and thicknesses are symmetrical as well as the glasses. And we're going to constrain, again, our focal length, our focal lengths, or back focal length, effective focal length. And to start with, we could make our buried surface a flat surface. However, later on, you may need to force its radii of curvature to get a solution that is desirable. And again, don't worry about spacing yet. So now we're going to get into some fun here. We're going to begin optimizing across a field. It's best to start with half your field of view, not jump up to your full field of view, just to get your solution somewhat dialed in. And once you get a reasonable solution, you can increase the full field. You'll need to add color at this point. Everything up to this point was monochromatic, so you'll need to add your FDC wavelengths to start with. And in terms of optimization, again, fixing our back focal length and effective focal length, and we'll need to use our pickups to maintain symmetry. In this step, we can vary stop spacing, but make sure it doesn't get too spread apart. Try to keep the lens package tight at this point. You can increase that spacing later. And we're going to optimize for RMS Wavefront just with the default merit function in your lens package, lens design software package. I use Zmax. And we can play with our meniscus thicknesses here to make sure that we don't have negative edge thicknesses and other nasty things. And we may need to force some curvatures manually. So you just need to be patient. You just need to guide your lens design software. And brute force is generally effective here, but you do need to be patient with it. So finally, we can jump ahead to our asymmetrical solution, and you can see our fields are really starting to come together, even at the full field of view. And we've added some new fields here. Notice it's good to have. You need to have an adequately sampled field to get effective balancing of your higher order aberrations with your fourth order aberrations. So make sure you have at least 5 fields in your optimization routine, and you may need to increase. It's actually, I recommend as many rays as it takes. This will slow down your software package, but it generally leads to a better solution if you increase the number of rays you're drawing. And you may need to increase your wavelengths. I recommend 5 just to get good sampling. And at this point, I split the first meniscus, and that really improves performance. And we optimized here by varying all radii of curvature. So there's been 14 variables to produce this solution. And so there's 10 curvatures, that's all of them. There's 2 thicknesses. We varied the thickness of the positive component of the meniscus and the air spacing between the stop. And we've fixed the total length of the lens. So that's the vertex distances between the first and last element. We have varied the thickness of the outer positive elements and the total thickness of the meniscus. We've actually maintained that. So you can increase the thickness of the positive component. And finally, we can do some fine tuning. So fine tuning, some fine tuning you could do. You could vignette the pupil, and that's often done in these fast aperture lenses. And what that does is it allows you to balance in the central portion of the pupil. However, you got to bear in mind that your vignetted pupil produces an almond shape. You don't clip the entire field, and I'll show you what that looks like in the performance slides coming up. And you can vary thicknesses. You can play with the total thickness of the lens. You can substitute glasses. You can optimize for MTF. You can reduce lens stress. I did that in this example. I made some surfaces flat, particularly the buried surface in the second meniscus and also the first element, second surface of the first element. It looks like we could probably do that on the last surface, last element. That just reduces manufacturing costs. We can increase the aperture to beyond f1.8. And to do that, you'd have to add elements. The 7th element generally will allow you to lower the f number down to f1.4. You could add A-spheres. That'll also allow you to increase the f number. The modified double Gausses that are getting down to below f1 or thereabouts, they have at least an A-sphere surface. So in terms of wavefront performance, there's wave fans here for all 6 fields, from 0 to 21 millimeters. And you can see that there are high order aberrations that are being balanced with 4th order aberrations. You get a lot of wiggling in your wave fans. So at this point, there's really nothing analytical about it. It's all driven by the optimization routine in your lens design package. So here's the pupil at the 21 millimeter image height, and this is the almond-shaped pupil that I was describing earlier. So when you're vignetting, you're clipping the bundle of rays, and you're doing it by clipping it into this almond shape. So you end up throwing away. You could throw away some of the aberration in the pupil out at the top of the bottom, and that's the tangential field. But in the sagittal field, you can't vignette that portion. So at this point, you're really limited by your higher order aberrations, and this is a perfect example of based on this pupil, all the complexity in the wavefront there. In terms of MTF, we have exceeded the performance of the Canon lens, but we've used very high index glasses to do that, so that's not surprising. So we even have some MTF out to 60 cycles per millimeter, but we're maybe 25 to 50% higher contrast across the field at the 10 and 30 cycles per millimeter lines. So in conclusion, the Double Gauss is it's an ideal lens if you're a new lens designer to learn and understand and begin playing with your lens design software. I recommend doing this from scratch, starting with the paraxial model and working your way up in complexity. It's a very good procedure to learn. So I hope you learned something. Thank you very much.